Welcome to our first lecture on machine learning. I'm Frodenz Labs, and today we are diving into the world where computers learn from data, solve problems, and even outsmart cats. Let's kick things off with a scenario you'll recognize. Imagine you hire an intern to sort emails into work and spam. They spend days spotting patterns, like phrases such as, "Congratulations, you've won," or "by now," until they become an email sorting pro. Now, replace that intern with a computer program. Feed it labeled emails, and voila, it learns to classify new emails on its own. That's machine learning in a nutshell. Think of teaching your cat what dinner time means. At first, they are clueless. But every day, you say dinner time and show them food. Over time, they learn the connection, dinner time equals food. Soon, they sprint over at the sound of those words, even before you pull out the bowl. This is exactly how machine learning works. The cat is the model, your words and food are the data, and repetition teaches it to act smart. Machine learning, as Herbert Simon defined it, is about systems improving performance through experience. Instead of coding every rule, we let computers learn from examples. It's like teaching a student to recognize patterns in photos or diagnose diseases by showing them thousands of cases. At its core, it's a subset of AI where algorithms learn from data, recognize patterns, and make decisions, without being explicitly programmed. Why all the hype? Think of ML as a Swiss Army knife for tech. It does almost everything. It automates repetitive tasks like tagging photos on social media. It powers personalized recommendations on Netflix. It scales to analyze millions of tweets in seconds. It even solves complex problems like predicting diseases, detecting fraud, or driving cars autonomously. The applications are endless. Let's rewind to ML's origins. 1950s, Alan Turing's Turing test and Arthur Samuel's checkers program laid the groundwork. 1980s, neural networks got a boost with backpropagation. 1990s, data-driven methods like support vector machines took center stage. 2000s, big data fueled Amazon's recommendations and Google's search algorithms. 2010s, deep learning exploded with self-driving cars and Siri. Today, transformers like GPT and generative AI dominate, revolutionizing creativity and automation. Let's decode some words. Training data is the examples used to teach the model. Testing data is the final exam to check how well the model learned. Features is the input variables, like age or income. Labels is the outputs we want, like spam or not spam. Model is the brain of the system, built by learning patterns in data. Scikit-learn is ideal for basic ML tasks, classification or regression. TensorFlow is a heavy-duty framework for deep learning. Google Colab is a free online coding environment for experimentation. Keras is a user-friendly interface for TensorFlow. Jupyter Notebooks is an interactive coding environment. Supervised learning is like learning with a teacher. You give it labeled data and it learns to predict new labels. An example is predicting house prices with input being size or location and output being price. Another example is a dog detector, showing 1000 dog photos labeled dog and 1000 goat photos labeled not a dog. Soon, it's a dog expert. In unsupervised learning, there is no cheat sheet here. The model finds hidden patterns on its own. An example is Netflix grouping viewers into clusters like action junkies, rom-com lovers, and documentary enthusiasts. Another example is organizing socks after laundry by group by color or size without anyone telling you how. Semi-supervised learning is a mix of using a little labeled data and lots of unlabeled data to train models, like classifying images with sparse labels. An example is image classification, in a scenario where only a few images are labeled but many more images are unlabeled. Semi-supervised learning can be used to train a model that can classify new images by learning from both labeled and unlabeled data. Reinforcement learning is a model that learns by trial and error, earning rewards for good decisions. An example is game playing, whereby in reinforcement learning, a model learns to play a game like Go by playing many rounds, adjusting its strategy based on winning or losing, ultimately improving its play to win the game more often. The steps in a typical machine learning workflow are as follows. In problem definition, you need to define the problem you want to solve. This includes identifying whether it is a classification, regression, clustering, or other type of problem. In data collection, data is gathered which will be used to train and test the model. This can come from various sources such as databases, surveys, web scraping, or publicly available datasets. For data preprocessing, first clean and prepare the data by handling missing values, removing duplicates, and correcting errors. Secondly, transform features to make them suitable for the model. Thirdly, split the data into training, validation, and test sets. Next is choosing the model. Select an appropriate machine learning model based on the problem type, e.g., linear regression, decision tree, random forest, neural network, etc. In model training, train the model using the training data. This involves feeding data into the model, adjusting its parameters, and minimizing the loss function. In hyperparameter tuning, you fine-tune the model by adjusting hyperparameters. For example, the learning rate, number of trees in a forest, or layers in a neural network in order to improve performance. In model validation, you need to validate the trained model using the validation set to assess its performance. In model testing, test the final model on the unseen test data to check how well it generalizes to new data. This step provides an estimate of how the model will perform in a real-world scenario. In model deployment, once satisfied with the model's performance, deploy it into production where it can make predictions on new data. This may involve integrating the model into an application or service. Let's get hands-on. Imagine predicting if students will pass an exam. Features might include study hours, attendance, and past grades. The label is pass or fail. We'd collect historical student data, train a supervised model, test it on new data, and deploy it to help educators spot at-risk students early. Every machine learning algorithm has three pillars. First, we have representation, which defines how the data is represented within the model. This includes selecting relevant features or transforming the raw data into a format that the model can process. Every ML algorithm has three key components. First, representation. This defines how the data is represented within the model. This includes selecting relevant features or transforming the raw data into a format that the model can process. Second is evaluation, which determines how well the model performs on both the training and test datasets. It involves defining a metric to measure the model's accuracy or effectiveness. Third is optimization, which is the process of finding the best set of parameters for the model. It often involves minimizing a loss function, which is the difference between the model's predictions and the actual values. Machine learning is everywhere. In healthcare, for diagnosing cancer from X-rays. In finance, for flagging fraudulent transactions in seconds. In retail, for chatbots answering customers 24/7. In entertainment, for Spotify's Discover Weekly playlists. In transportation, for self-driving cars navigating roads safely. But machine learning is not magic. There are several challenges, which include the data quality. Bad data produces bad models. An example is training a self-driving car with blurry images. It will think a lamppost is a pedestrian. Overfitting is another challenge. It involves a model that memorizes training data but fails on new examples. Bias is another challenge. If training data reflects human biases, models might perpetuate them. For example, favoring certain groups in hiring. Your turn. Think of a system like Netflix or Siri. What type of machine learning algorithm does it use? Share your thoughts in the comments and also brainstorm on how could machine learning reduce food waste in a cafeteria, maybe predicting demand or optimizing storage. The future of AI is in your hands. Thank you for joining this journey into machine learning. Stay curious, keep exploring, and remember, the best way to predict the future is to build it. Subscribe for more lectures, and let's learn together.